Okay, so we'll just continue today with our review of pre-calculus. Now, this next section will be a brief introduction and review, I guess, of linear functions, and that will be followed up by other more complex functions. But this part will go fairly quickly because we're already very familiar with linear functions and how they behave. But there might be some details in here that we've forgotten about. So pretty soon we'll be done with all this review and we can get started on limits. Now, by the way, I did get the limits notes posted onto Brightspace last night. So if you want to go ahead and start reading ahead, you can certainly feel free to do so. But when you start reading it, I just want to point out that it's a fairly complex topic, and you're going to find some of the discussion to be fairly, let's say, theoretical. But once we get to the practice problems. In other words, once we start doing actual examples, you'll find that it's not maybe as scary as it looks. Okay, the definitions, they can be very intense, but the actual topic itself of limits is not really that terrible, not terribly complicated, but we do need to introduce the formalities, and then we can practice with actual examples, and you'll see that for the most part, it's not that terribly complicated. Okay, so just like I said, when you start flipping through the slides, if it looks really overwhelming, um, don't be too concerned about it because we'll get used to it pretty quickly. Anyway, and then also I started to set up due dates for the assignments because I'm still learning the system. And I've made a mistake somewhere along the way. So at the moment, if you look in there, you'll see two homeworks related to limits that are due on the 16th of June, which, we could extend that a little if we need to, but I think that sounds about right where we should be by the 16th, which is a week from this coming Sunday. And there's meant to be two others as well, but I did something wrong. And so let's just say I'll get that straightened out very quickly. In the meantime, why don't we just focus our attention on what we're doing today? Now, of course, everybody remembers the equation of a straight line, y equals mx plus b, and m is the slope, and b is the vertical intercept. And by the way, this is not the only way we can write the express a straight line. This method is called the slope-intercept form. We'll review quickly the other form, which is called point slope. And the whole idea here is that when you look at this equation, it should be very clear what the slope of the function is and what is the intercept. So of course, m, the slope is delta y over delta x, which you could also think of as y2 minus y1 over x2 minus x1. And of course, with a straight line, the key is that the slope is a constant. It never changes. Unlike, let's say, a quadratic function, the slope changes continuously throughout that parabola, but here the slope never changes. So here's a quick example. Here's a classic example of a linear function, y equals x minus 7. So it's clear to us that the slope is the coefficient of x, which is actually 1. There's an implied 1 here. And then, of course, the intercept is this constant -7. And so what that tells us is that when you draw this thing, the intercept would be here. In other words, remember, this is where it crosses the vertical axis. This is the point where x is 0 and y is -7. The slope is meant to be 1. It's hard for me to draw it properly, but what that means then is that every time x increases by 1, y also increases by 1. Okay, so for a sketch, it's not too bad, but the whole idea here is that you can see that the slope is 1, meaning that x and y were increased by 1 unit each, and the vertical intercept is actually that point 0, -7. Now, we can find the equation of a straight line, as you know, or here, this is actually that same function. I did this in Excel, as you can see. So that I could write on top of it two different points. I don't think we can do that in Symbolab. And those are 2 points on the straight line. You can tell, like for example, let's think of this as point 1 and point 2. And so the slope is y2 minus y1 over x2 minus x1, which means 0 minus minus 1 over 7 minus 6, which is 1 over 1, which is just 1. The intercept you can see is right here. Now, by the way, how can you find that algebraically? Well, given that the slope is 1, what you can do is substitute either of these points into this equation. Let's pick the second one. And you'll see that 0 equals 7 plus b, which means minus 7 equals b. So we've done two things here. We solve for m equals 1, and we solve for the intercept, which is -7. And so if we only had the 2 points, we could figure out from that information that the actual equation of this line is in fact x minus 7. Okay, so here, yeah, just what I was saying. You can solve for the slope. By the way, I just want to point out here, it doesn't really matter which point is considered to be point 1 and which is point 2. As long as you're consistent, you'll still get the same answer either way, no matter which point is x1, point 1 and which is point 2. Okay, and then you plug one of them into the equation. Now, of course, you can tell by that slope, the sign of the slope, if the function is increasing, decreasing, or if it's a constant. So in other words, say you have y equals x minus 7. Okay, as x increases, y increases. But if you had y equals minus x minus 7, instead it would look something like this. And if you had instead a slope of 0, would mean you have something like this. As we have already seen, this is a horizontal or flat line with a slope of 0. That means it is a constant. All right, so here's another good example. Y equals 3x minus 2, which means that the slope is 3, the intercept is -2. And so you can see here's the intercept. Now the slope, you can tell, let's say, for example, if I pick 2 points on this line, let's say, well, it's hard to tell from this graph. Let's just say when x is 1, just by looking at this function, you can see that y is going to be 1 as well. Okay, if I plug in 1 here, I'll end up with 3 minus 2, which is 1. So, and this is a point, this is a point. And again, we can show that y2 minus y1 over x2 minus x1 is the slope. And that would be 1 minus minus 2 over 1 minus 0, which is 3 over 1, which is 3. And then, so now you know that y equals 3x plus b. And if I replace x and y with one of these points, let's say this one, that means that -2 equals 3 times 0 plus b, or -2 equals b. All right, so from any 2 points, we were able to figure out both the slope and the intercept. Now, of course, this one has a negative slope, which means that it's facing down. You can think of it as moving in a southeasterly direction. And so the intercept is 5. And the slope is -4. And you can see that as x increases, y decreases and vice versa. Now, here's a constant function. We've already seen this. It's just a flat line, and the slope is zero. Okay. All right. Now, this is the other way of writing an equation of a straight line. It's called the point slope form because it's explicitly written in terms of a point, x1, y1, and a slope m. The intercept is missing, but it's implied. It's implied by this equation. It gives us the same information in a slightly different way. In a way, it's comparable. I think I've used this analogy before to knowing the temperature. Let's say 0 Fahrenheit is, sorry, 0 Celsius is 32 Fahrenheit. They're different numbers, but they're telling us the same thing. And the same thing is happening here. Now, for some purposes, this might be more convenient. Although, let's face it, most of the time we see straight lines written like this. But it's good to know that there's another way of writing this equation. And so that means this is our slope, y minus y1 over x minus x1. So let's say we have this function. It's written in point slope form, y minus 4 equals 2 times x minus 5. So what we could do is, if we would prefer to write in the traditional slope intercept form, all we need to do is a little algebra. Okay, so we'll see on the next slide that here's what we're doing. We're adding the 4 to both sides, multiplying this 2 by both x and -5. So we have 2x minus 10 plus 4, and this is the final result. So it's hard to tell by looking at it, but these are the same straight line. So we're going to take this as our example. Our next example, we have an equation with a slope of 3 that passes through the point 6, -1. So we know m is 3, y1 is -1, and x1 is 6. We can use that information to come up with the equation of the straight line, both in the point slope form and in the slope intercept form. So how do we do that? All right, well, again, this is the point slope form. So we were told that y1 is -1, x1 is 6, and the slope is 3. All right, so we make some substitutions. Now, of course, we can do some algebra. Y minus minus 1 is 1, y plus 1. Here we distribute the 3 across the x and -6 to give us, on the next slide, y plus 1 equals 3x minus 18, or finally, when we're done, we have 3x minus 19. Excellent. So now, oh, what a surprise. We have a third format here, the so-called standard form, ax plus by equals c, where you don't really see this one very often. Here's the 2 points. So we're not going to really use this form, but we're going to instead take 2 points and use that to determine the point slope form. So we got x1, we've got x2, y1, y2 from those 2 points. Okay. And we plug these in to this equation for the slope. We get a slope of 1/3. So that means now we have 2 points. We just need one of them. We can pick either one. And so this is going to lead us to the point slope form of this straight line. And you can see it's right here. Just by direct substitution. This is our point slope form. Although here you would, of course, write this as just x. And then this, after doing some algebra, you can see this is the slope intercept form. All right. Now, here's a quick application of this. This is something that you would have seen if you'd taken a course in microeconomics. Microeconomics lends itself very nicely to calculus applications. I mean, microeconomics ultimately is heavily, or I should say, closely related to calculus. Not so much macro, but micro, a lot of the concepts you learn in microeconomics can all ultimately be expressed in terms of calculus. So here, for example, we have a cost function. Okay, now in economics, we assume that all costs of production either are fixed, which simply means that they're not dependent on how much of a product we're making, or else they're variable, which means they are dependent on how much we're producing. For example, at a Starbucks, the variable cost would include things like the coffee beans, the milk, the sugar, the cups, the lids, everything that goes into the production of a single coffee to be sold to a customer. The things that do not depend on the output would be things like the rent, okay, or property taxes, whatever the case may be. So in order to figure out how much it costs to produce a given number of units of your product, we need to take into account both fixed costs and variable costs. So for this case, we were told that the fixed costs are 1,000. 100 is the variable cost. X is the number of units that we produce, and Y is the total cost of producing these units. So we end up with 100X plus 1,000. And if you notice here, if X is 0, we don't produce a single unit of this product, we still have to pay the $1,000. Okay. So this is how much it costs to produce X units of our product. If we produce 20 units of the product every month, well, it's pretty clear. I mean, we're basically evaluating this function at X equals 20. You could also rewrite this as and then we note that F of 20 is 100 times 20 plus 1,000. And that's 3,000. Okay. Now we can certainly graph this relationship the way we normally would. We would have an intercept and a slope. Okay, well, I guess I didn't do that in the slides, but you can see how easy this would be. Intercept is 1,000, and the slope is 100. All right. So now we're going to look at some different examples. Here's the function minus 2/3 x plus 5. Now, right away, just by looking at this, we know that it has a negative slope, but a positive intercept. So what you could do, if you're not sure what it looks like, is you could pick 2 points and plot them with a straight line through them. For example, here, if you just randomly pick 0 and 3, you can then solve for y or f of x. So this tells me that the 2 points that we have in our line are 0, 5 and 3, 3. And if you draw that, all right, well, it's not perfect, but you get the idea. Um, yeah, that could be a little straighter. And so it is a negatively sloped function. So, but you can tell because of the fact that x went up from 0 to 3, but y went down from 5 to 3. Okay, so this is our straight line. Now, sometimes we may need to find out what is the x-intercept, which is the horizontal intercept, um, not to be confused with the vertical intercept, which is where x equals 0. Here, we're looking for the point where y equals 0. So in other words, this is the vertical intercept, which means that x equals 0. And this is the horizontal intercept, which means that y equals 0. So this is a hint as to how you're going to find these 2 points. You're going to actually substitute in the first case for the vertical intercept. What you're going to do is find what value y has when x equals 0. And then for the horizontal intercept, you're just going to reverse that. You're going to set y equal to 0 and figure out what the corresponding value of x is. So like here, for example, we had this function earlier. We have a negative slope, but the vertical intercept is positive. This is what we're looking for right here. Where does it cross the horizontal axis? So that happens when y equals 0. So if you substitute a 0 here, now we can algebraically add 2/3 to both sides, 2/3 x that is. Whoops, sorry. Equals 5. Now, in order to solve for x, I'm going to multiply both sides by 3/2. So we end up with x equals 15/2. Okay, so this is the point. Oops. 15/2, comma 0. Or 7.5. Of course, it means the same thing. Now, two extreme cases are horizontal and vertical lines, which we've already discussed, but just a quick review. A horizontal line means that the slope is 0, and therefore, since m equals 0, that means that f of x simply equals b. On the other hand, if y is 0, which it will be at the vertical intercept, or the vertical line, then we have 0 equals mx plus b. Well, actually, here, there's no guarantee. No, this is just some random vertical line. This is not necessarily the intercept. So we don't know what it is. What we do know, though, is that there is no vertical intercept unless x equals 0. A is just some constant, and so it's a vertical line, which means, by the way, as you recall, this is not a function. It's a relation. Okay, and here we simply have, so here the slope is 0, and here the slope is undefined. All right, we've already talked about this, but it's good review. So there's x, y equals 0, 3 rather. And here's x equals 5. Okay. Now here's something you might not have thought about for a while. The concept of parallel and perpendicular lines. So parallel simply means they have the same slope. Okay, if you recall. Let me just throw a quick sketch up there. So, I mean, to the extent that they're drawn properly, these are parallel lines because they have the same slope. And the significance of this is that they will never cross. This is the only time that lines will never cross. Normally, they will eventually cross, but when they're lines, when they're parallel, meaning they have the same slope. For example, this might be where the intercept is zero. You can see they're only different by constant. The line on top is always two above the one below. So these lines are said to be parallel. And you can tell that they are because they have the same slope. And again, that implies that they never cross. Now, perpendicular means that they cross, but at a right angle. Oops. I'm still waiting from Wacom to tell me how to fix my tablet. I'm using this other one that I'm not as good with. So here's the two lines. And so there's a 90-degree angle where they cross. Okay. This is what it means to be perpendicular. So how do you know that two lines are perpendicular? Well, it's easy with parallel. Perpendicular is a little bit trickier, but not very difficult. All you have to do is look at the slopes. Actually, so here's some examples with parallel lines. With perpendicular lines, what we need is that the slopes have to have a product of -1. Okay. Or think of it this way. 1 over A is the multiplicative inverse of A. What we're seeing here is that the slopes are the negative multiplicative inverse of each other. Whoops, sorry. And like, for example, you're seeing here 2 and -1/2. Those are negative multiplicative inverses of each other. And the consequence of this is that their product is -1. Okay, so if the two lines have slopes whose product is -1, that tells us that they are perpendicular. All right, so not multiplicative inverses, but the negative. Okay. So now here's a graph of what we just saw here. This is 2x and -1/2 x plus 8. So and this one is y equals 2x plus 4. So you can see that they do cross. Where they cross, it's a 90-degree angle. Okay, and that's what it means to be perpendicular. Now, this concept of being perpendicular, it turns out to be very important in certain disciplines like if you're a math major, eventually you'll find yourself in a course called linear algebra. And this turns out to be a hugely important idea in linear algebra. But for now, it's enough to notice that we have two lines that cross at right angles. Now, we know, like we've just gone through saying, that unless two lines are parallel to each other, they must cross at one single unique point. One point, that's it. It can't be more than one, otherwise that means they're not straight lines. The question is, how do we find that point? Okay, good question. How do we know where they cross? For example, here's two lines. Now, first things first, you notice they're not they're not parallel because the slopes are different. They're not perpendicular because -2 times 3 is not 1. Okay, so these are neither parallel nor perpendicular. Okay, so what we're basically going to do, and by the way, what you're really doing here is this. At that point, what you're basically doing is you are finding where the two equations equal each other. Uh, that's the key to the whole thing. So in other words, what you're doing here is saying, well, at this point, the functions have the same value. So here we can solve for the x. And once we have that x, we can find the corresponding y from either of these two equations. All right, so let's do this. So we set them equal to each other. We do a little algebra. I add 2x to both sides. So I've got 8 equals 5x minus 9. I add the 9 to both sides. 17 equals 5x. 17 fifths equals x. So if you come back here, we know that x is 17 fifths. And now I can plug that into either of these two equations. It doesn't matter which one, and I'll get the appropriate value for y. Okay? And so it turns out to be 6 fifths after you do all the algebra. So we can come back here and put this in. And so now we can see that the point at which they cross is 17 fifths, comma, 6 fifths. All right. Okay, here's another quick example, another blast from Basic Micro. We have a sporting goods company selling football helmets. In order to produce these helmets, they pay a fixed cost of $250,000 per year. And then on top of that, each helmet has a variable cost of 120. So we know that the total cost function is y equals 120x plus 250,000. But now we're being told how much revenue they bring in. Each football helmet that is sold brings us $140 worth of revenues. So we define a total revenue function. Remember, X represents the number of helmets that we either produce or sell. So we have two functions. How much does it cost to make the helmets, and how much revenue do they bring us? So here's an interesting question, and this is very important to the owner of this business. What is the break even, meaning where our profits are zero, level of output? In other words, how many helmets would we have to make for our profits to be exactly zero? Well, we're going to do just what we did a few minutes ago. We're going to set these equal to each other because breaking even means that's where the total revenues exactly match the total cost. So we're going to set them equal to each other, and we determine that if we make 12,500 helmets, we will break even. Now, at that point, we can solve for either the total cost of the total revenue if we choose to do so. In fact, it looks like we've done exactly that here. So with 12,500, the total cost is 1,750,000. And then you can see from the revenue function, the revenues are also 1,750,000. So this is what we mean by break even. And then here's the graph. Now, again, this has been done in Excel, so it's not ideal, but here's 12,500, our break even point, 1,750,000. Now, from the company's perspective, though, if you notice, the blue line is revenues. The orange line is costs. So if they keep making more and more helmets, you can see that because the blue line is above the orange line, this is where we're making profits. Break even here, profits are zero. Down here, I guess you could think of these as negative profits or losses. Okay, so that's how this works. And again, it's easy to do this because these are both linear functions. In practice, they're often not linear, and that makes things more complicated, but it's the same basic logic. So this company knows that in order to make money, they better sell more than 12,500 helmets every year. The more, the better. Okay. Now we're going to revisit our old friend, the polynomial. Now, the word polynomial simply means many terms or many numbers. And you can see that unlike, well, these indexes represent the exponent. You notice they match each other. So that means that a cubic function like this wanted to, we could rewrite this as a3 x cubed plus a2 x squared plus a1x plus a0 to be consistent with this. And so what we're seeing here is that a cubic function is a special case. It is a polynomial of either order or degree 3, it's sometimes called. Okay, either way, whether we call it the degree or the order, it means the highest exponent in our polynomial. And then similarly, a quadratic function which again, if we wanted to, we could rewrite this as a2x squared plus b1x. Oh, sorry, a1. What am I saying? A1 plus a0. It is again a special case of a polynomial. They're both examples of polynomials. And then you can go on, you can have x to the fourth, x to the fifth. They all have their own names, by the way. After quadratic, we have cubic. Number 4 is quartic. After that, I'm not sure what comes after that, but we can look it up if we want to. Wikipedia has a page somewhere that has them all listed. In practice, we don't normally go beyond 3. It's very unusual to find real world things that can be measured with quartic functions, certainly not in finance and economics. Even the cubics are very unusual there. Normally, we have linear equations and we have quadratic equations. Okay, so again, we can call these degrees or sometimes they're called orders, and that's referring to the highest exponent in our polynomial. Now, there's just one thing, though, we have to watch out for. The exponents are restricted to being non-negative integers. Okay, so that means the exponents uh, 0, 1, 2, 3, 4, etc. Anything else means that whatever this function is, it's not a polynomial. So these, now if you look at these carefully, you can identify which ones are and which ones are not polynomials very easily, because if you look here, the exponents are all positive integers. By the way, don't forget, 9 is the same thing as 9x to the 0 power. So this qualifies because, remember, we were told that the exponent has to be non-negative. So 0 counts, and therefore constants count as well. Now, this one is okay. If you notice there's a negative here, that doesn't make any difference. All that matters is the exponent. Here, this exponent is implicitly equal to 1. And here, like I said, this one could be thought of as an exponent of 0. But here we're in trouble. Oh no. This one is not a polynomial. Because one of the exponents is -2. That's all it takes. We don't know what it is. I'm sure we could find a name for it, but it is not a polynomial. I'm sure the graph is very bizarre. Polynomial graphs tend to be very well behaved. Something like this. Well, you know what? Just for the fun of it, why don't we go find out from Symbol Lab? It's going to be very strange, most likely. Let's see. All right, what do we have here? 4x to the -2 plus 5x squared plus x minus 5. Yeah, I mean, that's pretty bizarre. I figured as much. There's no way this is a polynomial. Polynomials are nice. Like, for example, if I just got rid of this part, it's so straightforward. Look at that. Yeah, that's what we like. That's a polynomial for you. And if I add a cubic term here, you'll see it's still going to be very nice looking. Oh yeah, that's a nice function. Look at that. So you can sometimes, I mean, you can tell often just by looking at a graph if it's a polynomial or not. All right, now the degree, it's easy. Now, by the way, this is one time when I remember I mentioned that by convention, we always write these terms starting with the highest exponent down to the smallest. What we're about to do is one of the reasons why. When we look at this polynomial, we often want to know what degree it is. If these are in some random order, it might be harder to find out what the degree is. Here it's very easy. Here it's 4, here it's 7, and here it's 5. And it's easy to see because we've written it in the correct order. So there's one benefit there to being neat and following the rules. It makes it harder to make a mistake. Okay. Then we also have this notion of the leading coefficient. It's very straightforward. All it is the coefficient of the term with the highest exponent. So in other words, here we would have the 5, 9, and -8. That is defined as the leading coefficient. Okay. Now we're going to turn our attention briefly to quadratic functions. Now we already know that word quadratic means that it is of degree 2. Okay. It is represented as a parabola, which itself is always symmetrical about symmetrical in the sense that no matter where we draw it, this is our vertex right here. This line is called the axis of symmetry. And that means this side is a mirror image of this side. Okay, so this is true for all parabolas. Okay, we have this property of symmetry, and it looks like a U. Okay, um, not exactly. I mean, yes and no, because normally U might look like this. If you the U, it looks more like a bowl, and this because the values are increasing forever. The letter U, that's not really happening, is it? These lines are basically going straight up. So it's not technically a U. It's more like I think a bowl is a better way to describe it. Now, we've already discussed this before. If that coefficient or the leading coefficient is positive, the parabola opens up. And if the leading coefficient is negative, it opens down. So that part is easy to tell just by looking at the equation. If we have a zero, then of course we no longer even have a quadratic function. It is now a linear function. So we're going to briefly look at the components of a parabola. The vertex we've already seen is either the minimum or maximum point. And we know that it has to have one because of its shape. In other words, you're not going to get something like this, a flat bottom or some nonsense like that. It's going to have one unique minimum or one unique maximum, and it is formally known as the vertex. And as I mentioned yesterday, um, if the parabola faces up, the vertex is the minimum point. If the parabola faces down, of course, the vertex must be the maximum point. But there has to be one, and there's one unique vertex. The axis of symmetry I just showed you, if you drew a line through the vertex, then the parabola will be the same on either side. The solutions or zeros are where it crosses the horizontal axis. And of course, there's always going to be a y-intercept because it has to cross the y-intercept because the range of the domain are all the real numbers. Okay, now, by the way, remember we said before that there's two different ways of writing a linear function. We have the point slope form, which is what we're not used to, and then the slope intercept form, which is what we're more used to. The same thing is true for a parabola, or rather a quadratic function, which is expressed as a parabola. You can write it like this. But we have another alternative version of this. This is the so-called vertex form. Now, remember I mentioned, I think yesterday, that the vertex is always written as h comma k. So what you're seeing here is that the vertex form shows me the x coordinate of the vertex and the y coordinate right in the equation. So I can identify it directly just by looking at this equation. And of course, this is just an algebraic rearrangement of the traditional form. But for some purposes, this is more useful. Let's run through a quick example. Okay, so here we have the quadratic equation written in our preferred form. Here's A, here's B, here's C. Okay, so it turns out that there's a formula. Now we know that it's facing up because A is positive. We also know the intercept of this, the vertical intercept that is 7, meaning that it cuts to the point 0, comma 7. How do we know that? Because if you replace these x's with zeros, the function will be equal to 7. That's, it looks like the way this thing has been set up, this is also a vertex. No, not necessarily. Sorry, that's because of the way I drew it. That doesn't necessarily have to be the vertex. It is the intercept, but it may not be the vertex. In other words, if it looks like this, the vertex could be over here, even though this is my intercept. So don't be deceived by my little sketch here. Okay. Um, so yeah, this is the Excel graph of it. It looks like, I'll tell you, let's do this in Symbol Lab. Because the symbol lab will identify exactly where the vertex is. All right. My mouse is acting up now. I mean, it just never ends. I'll tell you what. It just never stops. Yeah, it was working 2 seconds ago. Unbelievable. Oh my God, it's actually working now. All right, here we go. Let's do this. 2x squared minus 6x plus 7. All right, I just want you to be able to see very clearly where the vertex is. Oh man, my graph was way off. Oh my God, I really did a terrible job of this. All right, I did. See this one. No, but see the problem with this one is that I just realized that it shows the intercept is negative when it's actually positive. So in other words, what we really want is this, something like this. That's the vertex. The intercept is 0, comma 7, but it's way over here somewhere. All right, now we're in good shape. Now, of course, it's very helpfully showing it to us. It's like we don't even have to figure it out ourselves. The vertex is 3 halves, comma 5 halves. Now let's see why. Well, luckily for us, there's a formula we can use for this. Well, that takes care of that. Now, K is f of h. In this case, f of 3 halves, which means 2, 3 halves squared minus 6 times 3 halves of 7. Oh, now 6 times 3 halves is minus 9. Or actually, I'll tell you what, let me write it like this first. Minus 18 halves plus 7, which is 18 fourths. I'm going to need another slide for this. Hold on. That's better. All right, so let's try that again. All right, so we have 2 times 9/4. Now here we have 18 halves, 18 quarters. So for something like this, what we usually do is try to find a common denominator. So here I'm going to rewrite this as 36 over 4 by multiplying it by 2 over 2. And then here that makes this 28 quarters. And so this is 18 minus 36 minus 18. This is 10/4, which is 5/2. That's the value of K. So H is 3/2. K is 5/2. So our vertex is this point. Just as Symbolab predicted. So this is what we have now. Oh, by the way, the A is the same in both forms. So remember, we saw that A is 2. So whether we're using the traditional form for our quadratic equation or the vertex form, A is still the same. Okay, so this is the final result. 2 times x minus 3/2 squared plus 5/2. Now, if you want to, you can prove to yourself by multiplying this out and adding up all the terms that this actually just brings you back to this, 2x squared minus 6x plus 7. Okay, they're algebraically equal to each other. Now, I mentioned this a couple of times, the axis of symmetry. If you notice, basically, this is just a vertical line through H. Because this is the formula. Remember, the formula for H is minus B over 2A, which so that X, by calling it this is the vertical line X equals H. That's the so-called axis of symmetry, and that defines where the function is symmetrical. Okay. So here, for that graph we just saw, the axis of symmetry is x equals 3/2. Okay, so that's very straightforward. And then this is what it looks like in Symbolab. And again, all right, I didn't draw it as well as I might have, but the two sides are identical to each other. It's like identical twins, I guess, looking in the mirror or something. All right, now how do we find the solutions? By the way, I think I've mentioned this already. With a parabola like this, the solutions are the points where it crosses the horizontal axis. Unfortunately, though, sometimes it doesn't cross. In the case like this, the solutions are imaginary. So we're going to focus our attention on real numbers. So we're going to assume when we start out here that we have something like this, okay? This case over here. So basically, the A's, B's, and C's are taken from this format for a quadratic equation. And you just plug everything in and you're all set. So for something like this, x squared minus 3x minus 4 equals 0. A is 1. There's an implicit 1 here. B is -3. C is -4. So you plug everything in. Now, here's where you have to be careful. There's a lot of negatives floating around here. It's easy to make sign mistakes with this formula. And if you find yourself with a negative number under the square root sign, you'll, at least for this class, you'll know you've made a mistake. Okay, because we're not going to have any imaginary solutions here. So you end up here after all the dust settles with positive 3 plus or minus square root of 25. Now here we got lucky. When you see something like this, it means we have a nice, probably a very nice solution, not some messy thing like radical 13. And so keep in mind, this tells me that I'm doing two things, 3 minus 5 and 3 plus 5 all divided by 2. So this reduces to minus 2 halves, positive 8 halves, which in turn reduces to minus 1 and 4. So if you plug this into Symbol Lab, you'll say, oh, I see what you mean, because it's going to identify those points for us. All right, was it x squared minus 3x plus, minus 4. And you'll see it's going to find those points for us. Okay, right there, negative 1, 0, 4, comma 0. Those are our two, the solutions are the x coordinates, negative 1 and 4. Okay, so it's typically will identify for us the two solutions, the vertical intercept and the vertex. There's more if you ask for it, but this is what it normally does. Well, here's another example in case you need the practice. A is 1. Remember, there's an implicit 1 here. B is negative 6. And finally, C is 8. All right, so we do some plugging in. And you can see we end up with 2, comma 4. Oops. So in other words, the graph will end up looking something like this. Because, in other words, we have two positive solutions. All right, so there's a few more details here we want to consider. I'm trying to see how far ahead we still have to go here. By the way, I do want to quickly review trig functions as well. I don't want to neglect that because we will need them. There's some interesting stuff here. We'll be looking at it in our next session. I'm trying to get a sense of how much further we need to go here. Probably the rest of this can be knocked off next time, and then the time after that, we'll do some trig functions, and then we can start our limits. Okay, so I'm thinking, well, we still have some interesting stuff to do here. We have to spend some time looking at logarithmic and exponential functions because they're awfully, awfully important in calculus. So we've got a little ways to go. I'd say maybe 2 more sessions and then we'll be done with our review. And then we can start looking at limits. Okay. So because of that, I'm going to have the due date for those limit homeworks a week from Sunday, which is the 16th. I think we can do that. If not, I'll just change the dates. But I think for the time being, I'll set those as our dates. So if you look at them, you'll see at least the first 2 are already listed. The other 2, well, we had a problem there. So, all right, we'll stop right here. And so the next time we meet, we'll just wrap up at least this part of the review. And then when we're done with our trig review, then we can go ahead and start limits. All right. So I'll see you all next time.